What does the formation of a black hole look like? How do we get from this to that? Until the 19th century, the fall of bodies and the orbit of planets were modeled by Newton's theory of gravitation. It was accepted that objects were attracted to one another and that they were subject to a force, gravity. At the dawn of the 20th century, Albert Einstein published his general relativity. According to Einstein, the fall of bodies and the orbit of planets are not due to a force, but to a curvature in the very fabric of space and time. Objects follow straight lines within a curved spatium. For years later, Arthur Eddington would successfully prove this theory experimentally. During a research expedition, Eddington measured the positions of distant stars whose light passed close to the Sun. He was able to distinguish them thanks to an eclipse. When passing near the Sun, light rays are slightly deflected by the curvature of spatium and the image of the stars appears shifted. This is known as gravitational lensing. Newton's theory of gravity also predicted that light rays would be deflected, but relativity predicted a deflection twice as strong, which Eddington was able to measure and attest. Thus, due to spacetime's curvature, the images of the stars are slightly shifted near the Sun compared to their actual position. Here is a simulation of this effect as observed by Eddington. At this scale, it is very difficult to perceive. However, if the Sun were more compact, the effect would be more pronounced. We can observe this by shrinking the size of the Sun without affecting its mass and by bringing the camera closer. Here is what Eddington would have seen with a Sun 100 times more compact, 200 times more compact, 500 times more compact. At this stage, the optical distortion becomes clearly visible. With the Sun twice as compact, some stars even appear duplicated. The light is indeed so deflected that it can bend over and under the Sun and reach us. Let's push this even further. We are now observing a Sun 10,000 times more compact than reality. The entire sky appears to be split into two regions by an Einstein ring which contains copies of all the stars in the sky. It is even possible to distinguish stars that are actually behind us. In such wildly curved spatium, sunlight struggles to reach us. Light waves are stretched to such an extent that the intensity of the light we receive is reduced and the color of the star is shifted towards red because the wavelength is stretched. Thus, if it were again 15 times more compact, it would appear completely reddish and its surface would even seem distorted by optical effects. We could observe the north and south poles at the same time as well as some areas located on the far side of the Sun. Light could indeed leave the surface towards the back and then curve around back towards us. Finally, if our Sun were 230,000 times more compact than it actually is, if it measured only 6 kilometers, it would be completely invisible. Its gravity would be so great that light would no longer be able to escape its surface. We would see a black disk surrounded by a distorted starry sky. An infinite number of repeated images of all stars would accumulate and revolve around the central shadow. At this point, the curvature of spatium would be so intense that the star could no longer remain static. The Sun's surface would be forced to collapse in on itself, inevitably sliding along the curvature of spatium. Indeed, in this bubble-like region, the star's surface would have to move faster than the speed of light to resist collapse, which is impossible. It is an event horizon from which nothing can escape, a black hole. At the center, the Sun's matter condenses into a singularity, a microscopic region, but our current models still struggle to describe. Nowadays, we know that black holes exist and that they can indeed form through death of a star, the gravitational collapse of a star in on itself. In the case of our Sun, its mass is not enough to form a black hole. When it will have consumed all its fuel in 5 billion years, the Sun will expand and form a nebula, while its core will compress into a white dwarf, an object whose collapse is stopped by the collision of electrons with each other. At this scale, the particles refuse to pass through one another, which stabilizes the object. Some more massive stars collapse further. They explode and leave behind a neutron star stabilized this time by the collision of neutrons. If the initial star is 20 times as massive as the Sun, then after exploding, its remains inevitably collapse entirely, forming a black hole. An extremely fast process that lasts no more than a few milliseconds. During this phenomenon, the geometry of spatium changes inside the compressed celestial body. It eventually creates a horizon from which light rays can no longer escape. What would we see if we could observe with our eyes those final moments? The collapse of the star's core into a black hole. Let's open a quick parenthesis. The Oppenheimer-Snyder model. In 1939, Oppenheimer and Snyder studied this effect. They proposed a very simple model in which a homogeneous ball of pressureless matter collapses in on itself. Over time, the surface of the star collapses following a free fall trajectory and eventually creates a singularity. Using the equations of general relativity, we can determine the trajectories of light rays inside and outside the collapsing star. They bend outwards due to gravity. In particular, we see that as the star collapses, light rays have more and more trouble escaping to infinity. At one point, the curvature becomes so strong that the light ray never escapes. It stays stationed at a fixed altitude. Beyond this point, all light rays are forced to collapse onto the singularity. This is the black hole. Therefore, we see that the horizon of the black hole is formed by the trajectories of light rays. It emerges from the center of the star before it has even collapsed. Because after this precise moment, all light rays will be trapped. Collapse simulation. Thus, based on this model for the trajectory of light rays, we can simulate what we would see in slow motion when a star collapses. Initially, we see that the object would shrink. Gradually, the contraction would accelerate due to gravity. The surface of the star falls at an increasing fraction of the speed of light, and light itself has more and more difficulty reaching us. The star reans. This phenomenon is more pronounced in the middle of the image because this is the part of the star that will move away from us the fastest. The center of the image is also in the position closest to us. And since light rays take some time to reach us, we observe this place with less delay than the edges of the star. As the surface collapses, the image of the star unfolds, revealing its poles, then its rear. The evolution slows down and the star appears to freeze. Only a sliver of light remains around what is now just a shadow. Finally, everything fades away. In just a millisecond, a black hole has formed. Thus, when a celestial body collapses in on itself, its image seems to eclipse itself until forming the shadow of the black hole. Now, here is what we would see if the star were transparent and light rays could pass through it as it collapses. As it collapses, the star becomes increasingly dense and the optical distortion intensifies. Conclusion. Finally, if we throw an object into this black hole, the gravitational influence of this object also produces a lensing effect which dilates the image of the black hole behind the object somewhat like a magnifying glass. Viewed from outside, as it falls into the black hole, the object appears to freeze and darken. It becomes part of the shadow whose size seems to have increased. In other words, the shadow of a black hole is formed by the flattened images of all the objects it has captured. Seen from the outside, nothing ever crosses the event horizon. And everything is still there, frozen on this shadow.